All right, today we are going to tackle the biggest story ever told. We're talking about the 4 billion year journey of life on this planet. It's an epic tale that starts in the fiery hearts of stars and ends, at least for now, with us. We're going to trace this incredible chain of events that connects the very first simple cell to the dizzyingly complex world that we see all around us today. You know, this quote is the perfect way to frame our journey. When you look up at the stars, you're literally seeing ancient light from a past that's long gone. Well, in the exact same way, the study of evolution lets us look back in time not through the vastness of space, but through our own biology. It is the ultimate origin story, the one that explains the incredible, beautiful diversity of life that we see everywhere. So here's our roadmap for this immense story. We're going to start at the very beginning with the cosmic stage setting. Then we'll dive into one of science's greatest mysteries, how life first sparked into existence. After that, we'll look at Darwin's brilliant theory that explains how it all changes. Then we'll play detective and look at the clues life left behind. And finally, we'll zoom in on our own evolutionary story. Now, you might think our story starts here on Earth, but nope, it actually begins way, way before that, in the vastness of space. For life to even get a chance, a whole universe had to be born, and a very specific planet had to be forged in just the right way. Okay, just try to wrap your head around these numbers because they are absolutely mind-boggling. From the Big Bang, it took over 9 billion years just for our little planet to form. And even then, Earth was just a barren rock for another 500 million years before the very first, simplest forms of life even flickered into existence. I mean, we are talking about a timescale that is truly epic. So how do you turn a hot, molten rock into a living planet? Well, first, volcanoes just belched out this primitive atmosphere. Then the sun's intense UV rays did something incredible. They helped create an ozone layer, which is like a planetary shield. With that shield in place, the surface could finally start to cool down. And then it started to rain. And it didn't stop for centuries, filling up the basins that would become our very first oceans. All right, so the stage is set. We've got a planet, we've got water, we've got a stable atmosphere, but the show hasn't started yet. The main characters are missing. And this brings us to the next and maybe the most profound chapter. How did we get that incredible leap from simple chemistry to the very first living cell? This right here, this is one of the biggest questions in all of science. It's a real head-scratcher. Before we got to our current understanding, people came up with some, well, let's just say creative explanations. For hundreds of years, the leading idea was something called spontaneous generation. Basically, the idea that life could just, poof, appear. You know, frogs from mud or maggots from meat. It took the brilliant work of Louis Pasteur to finally prove that life only comes from other life. But in solving that mystery, he accidentally created an even bigger one. If all life comes from life, then where did that first life come from? And that brings us to the leading scientific theory today, chemical evolution. The idea here is that life didn't just appear in a flash. Instead, in this violent, energy-rich, primordial soup of early Earth, we're talking constant lightning, volcanic vents, simple, non-living molecules were slowly forged into the complex building blocks of life itself. And hey, this isn't just a wild guess. The famous Miller-Urey experiment put this idea to the test. They basically created a miniature early Earth in a flask, zapped it with sparks to act like lightning, and then they just waited. And what they found was incredible. Amino acids, the fundamental building blocks of all life, had formed all on their own. It was this huge aha moment, the first real proof that the jump from chemistry to biology wasn't just possible, it was actually plausible. So, life got started. But how did we go from a single-celled organism to the incredible variety of plants and animals we see today? That is where our next chapter and a man named Charles Darwin enters the story. Now, to really get how revolutionary Darwin was, you have to understand the idea he was up against. It was called special creation. This view said that life was fixed, that it was unchanging, and that it was all created on a very, very young Earth. But the things Darwin saw on his travels, especially in the Galapagos Islands, just didn't add up. He started to piece together a much more ancient and much more dynamic story of life. Darwin's absolute genius was in proposing a mechanism for how all this change could happen. He called it natural selection. And the logic is actually beautifully simple. First, you have variation in any population. No two individuals are exactly alike. Second, some of those traits are more helpful for surviving and reproducing than others. And here's the key.
Fitness isn't about being the strongest or the fastest. It's all about reproductive success. The fittest are simply the ones who leave behind the most offspring. That's it.
So really, it all boils down to two huge ideas. Think of branching descent as the pattern of life. It's like one gigantic tree where all living things are connected, with countless branches representing every species that has ever lived. And natural selection is the process. It's the engine that causes all those branches to grow and spread out and change over time.
Of course, a great theory needs great evidence. So now, we're going to put on our detective hats and take a look at some of the clues that evolution has left behind for us to find.
Okay, one of the absolute strongest clues is something called homology. The idea is actually pretty simple. You can see a family resemblance. It's when different animals have the same basic parts that they inherited from a common ancestor, but those parts have been modified over time to do different jobs. The underlying blueprint is exactly the same, even if the final house looks totally different.
This slide shows it perfectly. Just look at these forelimbs: a human hand, a cheetah's leg, a whale's flipper, a bat's wing. On the surface, they do completely different things, right? But look at the bone structure. Look at the colors. They are all built from the same fundamental parts. It's the same set of bones, just remixed for a different purpose. This kind of similarity is just powerful, powerful evidence of a shared ancestor.
We can also watch natural selection happen in real time. This is a classic example. This chart shows the peppered moth population in England before the Industrial Revolution. Back then, most trees were covered in this light-colored lichen, so the white-winged moths were perfectly camouflaged. The dark ones, well, they stuck out, and birds ate them, so the white moths thrived. Now look at what happened after industrialization. Soot from all the new factories covered the trees, turning them dark. All of a sudden, being a white moth was a terrible idea. You stuck out like a sore thumb. But the dark moths, now they were perfectly hidden. The tables turned completely. Predators picked off the white moths, and the dark-winged moths took over. It is a perfect real-world demonstration of how the environment selects for a certain trait.
And for our final chapter, let's turn this powerful lens around and focus it on ourselves. Let's trace the fascinating, twisting story of our very own origins.
So, the human branch on the tree of life starts way back, about 15 million years ago, with ape-like ancestors. The first huge leap was learning to walk upright. That freed up the hands, which paved the way for our own genus, Homo. We see Homo habilis, the handyman, making the first stone tools. Then comes Homo erectus, with a bigger brain, who likely controlled fire. And eventually we get to our closest extinct relatives, the Neanderthals, right before we, Homo sapiens, finally arrive on the scene.
Now, this number is fascinating. 1,400 cubic centimeters. That was the average brain size of a Neanderthal. And to put that into perspective, that is smack dab in the middle of the range for humans living today. It completely shatters that old stereotype of the brutish, dumb caveman, right? It paints a picture of a species that was far more sophisticated than we ever gave them credit for. And this is where our biological story really starts to merge with our cultural one. About 10,000 years ago, we invented agriculture, and that changed everything. For the first time, we didn't have to follow our food around, we could grow it. This simple shift allowed for permanent settlements, for bigger populations, and it laid the foundation for, well, all of recorded human history. We want to leave you with this one last crucial idea. It's so easy to picture evolution as this straight line, this ladder of progress, purposefully marching towards better and better organisms, but that's not what the evidence shows at all. It's a stochastic process, which is just a fancy word for saying it's driven by chance. Random mutations, unpredictable changes in the environment, those are the real drivers. There's no plan, there is no final goal, there's only the incredible, undirected, and frankly beautiful story of life, finding a way.